Testing, all right. Okay, I think we're live. All right, let's get started, everyone. So, it is now week 4 of CSE466, and we are just getting started with reverse engineering. So, as is tradition with everything in these classes, I would just like to quickly shout out like the top people from the last module. So, these are all the people with pitchforks next to your username. If you don't have a pitchfork next to your username, it's because you don't have an ASU email address registered to your account. So, congratulations to Ordinary, Combat with an 8, WD Bridge, Terminally Online. Keep pushing. Like, there's still a 3rd place finish available to be sniped by anyone in the class right now. And essentially, yes.
We can't go any higher. I can't go any higher because I'm just stuck at 37 because I already had 2 completions.
Ah, okay. That's something I'll fix for the next grades, because then that means in theory you might actually be higher than one of them.
I'm at 39, but it says 37.
Yeah, so this is just for the solves in the dojo. So because you carried them over, that's why. But I can fix that. So just in case, like you have been living under a rock, reverse engineering is now live. We've had a lot of people, classic, we add new challenges, the blue belts get mad because they have to go back and solve the baby challenges. And so we've added new cows and bulls. They're really great challenges, highly recommended checking them out. We put them right below Yon 85 in terms of the like quote unquote progression. I would say I think it's slightly easier than Yon 85 from like an approachability standpoint, but there's some implementation details that you might find challenging in these. So start early, use the Discord, ask questions, use your resources. Does anyone have any questions about the reverse engineering launch? Cool. All right. Remember, checkpoint this Sunday. Then it's due a week after that. So do not delay. And so pretty much I just wanted to hop straight into some demoing just because reversing is a very, very kind of time-sensitive skill, meaning the more you put into it, the better you're going to get. It's something that's very hard to teach. And so I'm going to try and give you some hands-on experience through osmosis. So, and to just quickly go over what we'll be going over, just some essential IDA functionality. I can also touch on Ghidra if we have Ghidra users. Just some general like reversing strategies and tips, the kind of things to prevent you from getting like stuck in random rabbit holes. Some common gotchas, some things that we see all the time that maybe you can avoid. And then finally, just some like ways that you can think outside of the box while reversing, because the most obvious solution is not necessarily going to be the one that is the most effective. So on our demo dojo, first off, the demo that I did last week, the leak to GOT demo, that's up. And then I've added a new demo called Reversing Roundup, which we're going to discuss today. So, let's see, does that freak out when I do that? No. Excellent. Okay. So, really quickly, just to give you an idea of what we're looking at. In this challenge, basically, we run file on this reversing roundup. We're going to see that we're dealing with a stripped binary. I'm not going to show you the source code. That's the whole point. And essentially, when we run this, we can see that we're presented with 5 different sort of mini challenges in one. And hopefully you pass all of them and maybe the flag falls out. So we're going to kind of dive into these one by one. And they're in an order on the menu. Yes.
I just on Twitch, and I noticed that you don't have the right screen showing right now.
I do not have the right. Okay, awesome. So when I go into full screen, it breaks. Noted.
No, I mean you just have different screens.
What? Ah, it's frozen. Excellent.
Yeah, I see some people. Like,
yes, thank you for that. It is frozen. Let's do that. Then let's try again. We love technical difficulties. Okay, and then in theory, if I switch back over here, okay, we're seeing that update. I'm hoping that's going to be fixed now. And then we'll just not go full screen. Resist the urge. Okay, so awesome. I'm seeing it updating on my monitor. So essentially, I created 5 little mini challenges, and each of them is designed to kind of highlight something that I think is kind of important in the reverse engineering process. And then kind of through it, we're going to go through IDA tips and tricks, just kind of figuring out things. So the one that I wanted to start with was actually the 5th one, which is misleading manifestation. And we give them all funny names just because we have to entertain ourselves somehow. But essentially what I want to do is figure out like what this is. Let's just do that, and then, so before you even start really going far, there's always some things that I'm going to run on binaries, like checksec. Okay, in this case, we're dealing with a non-PIE binary. I don't think that part's intentional, but canary found, NX enabled, partial rel row. Then similarly, also just running the challenge and seeing what kind of things happen. So in this case, if we go to 5, we have some mysterious text popping out. And then if we start feeding in input, something interesting happens. Assumedly, my menu is being dumb. But point being, things are happening. So what and why? So right away, when we're diving into IDA, let's see how much of this UI I can strip away, because I want to make this window as big as possible. So we probably don't need that. Can I get rid of that? Yeah, I don't need that. Basically just deleting random UI elements. Let's see. Maybe we can jam that somewhere else. Nope. All right. Looks like it's staying there. Okay, so the first thing I'm going to go ahead and highlight is just like some basic like hello worlds kind of stuff in IDA. All of our functions are going to be over here on the left, over here on the right in our main view. By default, it's going to pull up 5 different windows. Your main disassembly view, this is just called the IDA view. So basically when you're in the IDA view, hitting your spacebar is going to toggle you basically between a linear view and a more CFG or control flow graph view. So if we dive into a function with some branches going on, we can see that basically you can see our control flow represented in a graph. This is really useful when you have sort of common elements. For example, like large if-else blocks will very easily like just pop up in the CFG, loops in your code. So let's take a look. Like we can very clearly see that like I have a menu kind of big loop going on. Like we've seen a menu, we know what a menu loop looks like. And we can see that this is very hard to see because it's small, but essentially we have arrows that can indicate to us, hey, we're jumping back from the bottom of our code up to the top of our code. You can reorder your CFG and drag around your nodes at will. Personally, I'm more of a linear view kind of guy for most of the operations. That's just my preference, but you do you. Similarly, we have a hex view. This is just going to give you the classic like XXD output of your binary. We have a window for local types. This is going to become one of your favorite windows in all of IDA. We're going to go over it in a bit. And then finally, just some import and exports for symbols. I generally just close those 2 right away. So first thing I'm always going to do is just come in and find my main function. So over here on the functions list, when you're working with stripped binaries, you're going to notice that all of our function names don't show up anymore. Like I named all of these when I wrote my C source code and then I stripped the binary. So we're going to have to deal with some interesting challenges when we go through this. Now, the one thing I always like to point out when you're dealing with a stripped binary is IDA does a great job at identifying main. And this is because there's a great trick to identify main in nearly any binary, which is you find your libc start main function, which essentially this is going to be embedded in your binary like from the underscore start function. So it's a libc function. And essentially we're going to locate this and find our start function. So just to quickly go over what I'm doing, it's like when you hit a symbol in IDA and you put your cursor over it so it's highlighted like this, and then you hit X on your keyboard, you're going to see what we call XREFs or cross references to this symbol. So by hitting X on this, I'm seeing all of the locations in my binary where this symbol is used. Very, very, very useful just to quickly jump around the program of, oh, what's this? Where is this used? I hit X, I see all the uses pop up, and then I can start examining various uses to see, okay, here's what's happening. In this case, libc start main is only going to be referenced in start. Note that when you're in this IDA view, they'll also show up embedded in the disassembly right here. Or also I could hit X on this symbol and see that it's used in start plus 24. Now, the nice thing about libc start main is that if we hit F5 to decompile, the very first argument to libc start main is literally the address of the main function. And so we can always find it in our disassembler or our reverse engineering tools just by finding where libc start main is called and grabbing that first argument. This is something that also works dynamically. So if I came into GDB, ran this, and then I wanted to break on main, there's no main. And so instead, if I run, if I use, let's kill that. If I use start, it's going to break my program in that start function. And then if I just step down to where libc start main is, that first argument is the memory address of where that main function is. And that can kind of give you a good anchor point in the program to set a breakpoint and then begin exploring dynamically as well. So we found main. And now I've hit F5 to start decompiling things. So one thing I also like to do is just use multiple views at the same time. So one thing that's very nice about Ghidra is that when you launch Ghidra by default and you click on like a line in the disassembly, it'll show you, hey, here's the line in the decompilation that corresponds to this. You can also do this in IDA by synchronizing your views. So if we right click on our IDA view A, I go to this synchronize with entry right here. I can say, hey, I want to synchronize it with this pseudocode B window that I have on this other side here. And now, whenever I click on something in one, it's going to basically have parity in the other. So very easy way to not have to reason about, okay, what's this, what's that? Instead, I can just go, okay, where's this printf call? There it is. And similarly, it's very nice because if I mouse over a line, it's telling me, hey, this printf call in the decompilation is being represented by these 4 instructions here. Anyone have any questions about this so far? Yes. So all I did was I just dragged my tab around. So I just kind of picked it up with my mouse, and then I just kind of slotted it in next to one of these guys. If you're using like IDA on like your home system too, it's like you can drag these out, have multiple windows open, you can go crazy. One thing that I find useful when doing this is, oh, come on, dock back in. All right, we'll close it. Sometimes I like to look at the decompilation for multiple functions at the same time. Or another like common thing that we'll get to later is like, if I'm trying to reverse data types, I generally want to be able to quickly edit my data type while looking at the pseudocode that I'm like basing it off of. And so it's nice to be able to like throw your pseudocode window on one side, throw like maybe your like local types window on the other side, and like be able to reason about them at the same time. Let's see. I don't know how to get it back in there on here. Go. All right. It's fine. Oh. We're experiencing technical difficulties. There we go. We'll use pseudocode C. Synchronize that. Okay. So now let's actually start getting into this. So I'm looking at my main function. The question that I asked myself was that I wanted to look at this menu entry 5. And so I'm just going to come down here, look, okay, we see this menu entry 5 being printed out. We see a scanf, and then we see a very obvious like if block of just like, okay, here's the function that we're going down based on this menu entry. And so when I'm reversing, one thing that I'm always going to be doing no matter what is just constantly littering the program with assumptions. Now, this is something that can slow you down if you're making too many assumptions. Like it's very easy to accidentally reverse the whole program, and then you find out that like the exploit is just like a basic buffer overflow. And then you feel like kind of an idiot because you have all this intimate program knowledge that was ultimately useless. And so you have to learn how to strike that balance of like, okay, what do I need to reverse to understand the program at a detailed enough level to do what I'm trying to do? Like the exact specifics of how every bit in the input flows through the program end to end is not necessarily the understanding that you need to exploit it. So I'm just going to start hitting N on things to rename them. So in this case, I know that this was option 5 and we labeled this misleading manifestations. So maybe I'm going to say like menu 5 misleading or something like that, just so that when I look in the functions list, I can just go, okay, that's what that function is. Like, I don't even know what is in this function yet. I'm just labeling it for myself. Similarly, like you could go through and rename all of these at the same time. That's probably something I would do, but for the sake of time. So the first thing I wanted to kind of talk about is when can decompilation be dangerous? Meaning, just because I pull my code into IDA or pull my binary into IDA and I hit F5 doesn't mean that IDA is magic. Like, we're not going to be rebuilding the exact same source code that I built this from. And so we have to be careful because the only truth of what's happening in this program is over here in the disassembly or when you're concretely executing it in GDB and actually looking at it. Like you can get lied to in this decompilation process. And so I wanted to show an example of when decompilation can be misleading in a way that you'll actually run into on these challenges. And so in this function, we have a very simple check that we're looking at. We're looking to return v1 equals v2. So we've got v1, we've got v2, they need to be equal to each other. And so instantly my reverse engineering brain starts tracing back these variables, like where did they come from? And so if we look at v2, we can see that v2's usage is in a scanf call. And it looks like we are reading in %x, which if you haven't seen %x in a scanf call before, is a hex number. So right away, I'm just going to be labeling this, okay, input. And then similarly, v1, we can see that v1's coming from this function sub 401392. So we're going to click on in that, and we're just going to see, okay, this is returning a dereference pointer. Got it. So deref pointer. Then we can see a qmem copy going to v3. Now, right away, we can see here's one case of decompilation being kind of weird because I have this function called qmemcopy, but then I go over to my disassembly and there's not a single call instruction in sight. Does anyone know what happened here? So essentially what's happening here is IDA is recognizing an operation and then trying to put a function call there to make your life as the reverse engineer easier. For example, I'm sure you guys have gone through IDA enough by now to see like the high byte and the low byte shortcuts that exist for when it's trying to load like an upper or lower nibble. This is similar to that. And so we can take a look at this. We see XOR EAX, EAX, and then we're moving something, this 24H to RBP plus hex 10. And then we're moving this 68 string to RBP plus this var F thing right here, which if we look on the stack, we'll probably see what's actually happening there. Now, it's kind of confusing, right? Like these things don't like make intuitive sense the very first time you see them. And so I think it's important to be able to kind of concretely observe what's happening because you might see, okay, what is var 10? What is var F? And if we come up and actually look at them, we can see that basically IDA is replacing stack offsets. And so we're end up going to be putting these two values of this 24 and 68 in hex kind of right next to each other on the stack at some offset of hex 10 and some offset of hex F right next to each other. And so we could probably go into GDB and concretely observe that, but we're reverse engineering. Let's keep going. And so we can kind of reason about this. And so when I'm reversing, I'm always going to have something open to take notes. I think it's just something that you're kind of required to do. Meaning now, and you could put all your notes as comments like in IDA. Personally, I don't like doing this because IDA has a tendency to sometimes crash, especially like when you're working with like larger binaries and larger programs. Or like when we're playing CTF, like we generally have like IDA plugins that mess with IDA that can also crash IDA. And so keeping your notes external can be a good habit to get into so that when your IDA crashes or like you corrupt your IDB somehow, you don't lose everything. And to be clear, that's unlikely to happen in this class just because you're not dealing with those kind of like massive programs, but it can happen. And it has definitely like nuked CTF progress before. So we'll take a look here. So we're seeing qmem copy, $, and then this H value. So, and we discovered that that was 0x24, 0x68. And those are being thrown presumably into this v3 variable, which for some reason IDA is deciding is a character array of length 8. Okay, we'll get there. And then finally, we're going to scanf into this input, and then we're checking after we do this if this is going to work or not. So we put $H in v3. We call this dereference pointer function, which is just dereferencing A1. And so what does this mean v1 is going to contain? Yeah, so basically the data that v3 is pointing to, which because qmem copy like this, what do I call it? I guess like inserted like magic function by IDA that for convenience does take that pointer. And you could look up the definition of qmemcopy as well. Like it's a thing on IDA's docs. In fact, I probably should just show that. So if we look at qmemcopy on IDA, there should be, all right, well, there is a document somewhere that talks about this in detail. And so now let's try and like actually do this. So we know that there's this value of $H that we wrote down, that hex 24, hex 68. And we think if we just send it into the program, because it gets put to the location of V3, V3 then gets dereferenced into V1, and then finally we compare V1 against our input. So this should be pretty straightforward in theory. So we're going to run our challenge. I will probably run this with Python just so I can send in those hex values from pwn import star. And then let's say p.receive. And then we want to go to the menu entry of 5. We're going to receive again. We get that predict the mystery. So now, presumably based on our reading of the decompilation over here, we just ran this put statement. Now we're going to hopefully presumably be blocked on this scanf call. And remember, scanf is not the same as read. So if I just try to like P30 or P16 two hex values in to this %x, it's going to freak out a little bit. So you have to keep in mind like what input function you're actually working with. So I'm trying to input this value of hex 24, hex 68 in. How do I do that with %x in a scanf call? Like what is scanf going to be expecting from my input? Kind of. So it's going to be expecting bytes, but what bytes, like specifically? Because if I just try to do p.send, and then like traditionally we would just do like p16 and then this value of 2468, right? Or maybe, I guess since we're packing it, we'd probably want it to go backwards. But if I do this, then %x is going to freak out because %x is expecting like human input. And so what it's looking for is something more like this. I already forgot those numbers, 2468. So then we'll receive again. Oh, come on. Why are we blocking? What? All right. Why are we blocking? Did we exit? No. Okay, something happened. Anyway, but the point is that it's expecting a human readable value. So we'll try that 2468. And we're seeing that we're not passing this check. And so we could GDB this, we could go down, but the point that I'm trying to make here is that there is a lie that has embedded itself in this decompilation. And it's this deref pointer function. And if we go and look at this, we can see there is this very funny line of just return dereference A1 that happens to, oh wow, that went fast, that happens to correspond to, let's see, like 10 different instructions in assembly. And so what we're witnessing is IDA trying to make an assumption and something's going horribly wrong. And so this is the case where now we have to reason, okay, well, what's actually happening in this function? Like we can already see that there's a stack canary that's being like thrown in here at random that IDA's not showing us. That's this FS28 like stack check fail stuff. But then what are we actually returning? And so if we start tracing our data through here, we can remember that the first argument to our function is going to be RDI. And so we're going to drop it on the stack here. And so I'm just going to start writing things down because that's just kind of how I'm operating. So let's go. So RDI to var18. And then we can see we are putting our stack canary on the stack right here. So FS28 to RAX, RAX to var8. We can ignore that, zeroing out EAX, more ignoring. Then we're loading our value that we put on the stack into RAX. So var18 loaded to RAX. Then we are performing, oh, and so actually I've already made a mistake because we're loading it. And then we're going to dereference this pointer into EAX. So what's happening instantly? What value are we loading off of? I guess like how many bytes are we loading? Well, it's just a word, right? We see a word pointer. So we're actually moving 2 bytes here. So this line, move ZX, EAX, word pointer, RAX, is saying, okay, RAX currently contains a memory address. Grab the 2 bytes because of the word word that it's pointing to and put them into EAX and then 0 extend it, which is what that ZX is doing. So load 2 bytes from RAX to EAX, and then I just ZX, whatever, 0 extend. And so this is different from what the decompilation was saying. Like return star A1 is definitely different from what's going on here, just right away. But then we can see that there's even more going on. So we move this AX value into RBP plus var A. So who can tell me? So AX is going to be which of those nibbles in the RAX register? It's going to be the lowest one, second to last. And remember, if we didn't know that, we could look at a register table. So we're going to see that AX is referencing those 2 bytes. I went a little fast. Bytes 0 to 1 for 2. So we're putting those 2 bytes back on the stack. Then we're loading them again. And then, so ultimately, I don't want to give it away, but what's happening here?
We are extracting, let's say, I think we are pretty much just like getting the lowest 16-bit values and from the pointer that we pass.
So it might help in this case to actually just concretely observe it in GDB. And this is something that I will almost always do when the behavior's slightly like transparent like that, as in like, or sorry, not transparent, like opaque like this. Like you're staring at assembly, it's not exactly 100% checking out. Let's concretely step through and just see what happens. Like it's much easier to reason about something happening when you're looking at the results of what's happening in front of you. And so this is kind of where I want to introduce another little trick, which is how we can quickly start working with stripped binaries in GDB. Because like normally you would do this by coming in and trying to break on this function, right? But this function doesn't have a symbol associated with it in GDB. Like if I come in and try and break on like sub 401392, like nothing's going to happen. And so we have to be a little bit more creative than that. And so I'm realizing now that I built this binary with PIE disabled, so it's defeating the purpose of this. Like I could set like a concrete breakpoint, but let's say that we couldn't do that. And so what we can do is we can use basically the gef commands for PIE. And what this allows us to do is set breakpoints relative to the base address of the binary. And then gef will automatically recalculate the base address of the binary and then go in and set those breakpoints. And so I hope this works with a PIE binary. There's a 1% chance that it doesn't, and then I'll rebuild it, but that's fine. In fact, let's actually do that now. Might need to go into practice mode for this. Yep, okay. Mild technical difficulties. CD there. Do that. All right, check sec. No PIE still. What's going on here? That should not. GCC00. So strip that. Me when I can't type. Gotta do that. Okay, excellent. I don't know why this is. Let's see, it's FPIE. Oh, come on. All right, my genius students, who knows why this isn't working? Am I missing something obvious here? Okay, backup plan. We're going to the local dojo. Because this one also doesn't have PIE. What did I do? That's crazy. All right. Okay. We're not gonna argue about that one. So let's see. All right. So I'll demo this here offline, off the dojo demo, and then we'll go straight back. So when I run GDV and then I basically want to place relative breakpoints in the program, I can use these PIE commands. And I will mention that there is a man page for this. If you are interested and want to learn more about this, highly recommend the GEF man pages. So they're just online, just Google like GEF PIE commands. You will get a whole listing of everything that I'm about to talk about. And so let's go ahead and I need to get that address out of this binary. Tools IDA. 64. Give me that one. This and that. All right, sorry for the technical difficulties there. Don't know why I have two now, but okay. So I didn't start the binary, so that's okay. Anyway, so let's say that we wanted to break here. So we're in a binary, we're pretending it's stripped so that I can't just put a breakpoint on mysterious operation function. But what I can do is if I come and look at the address of where this is in the binary, this is at offset 1C80. And so what I can do is utilize this offset by coming into GEF, and note that this is a GEF exclusive feature. And I can go PIE break and then that offset that we just found, so 1C80. And then when I use PIE and run, note that if you just use the normal GDB run, GEF is not going to be alerted that the program started and not do the address calculation. The PIE run command is basically just a wrapper that tells GEF, hey, I'm running with PIE stuff going on. And so when I run this, file, Roundup, there we go. And so when I run this now, this breakpoint has been inserted automatically for us. So info B, that breakpoint is now automatically being calculated by GEF. Now, there's one catch to this, which is that if you try to rerun this program, you can sometimes run into issues where GEF is trying to insert multiple breakpoints. I think it's because I have symbols, it's being fine now. But if I didn't have symbols, you would have to restart and basically just delete all your breakpoints. And so the workflow that I'm kind of like have ingrained in my head at this point is you do PIE run, and then you do your stuff, and then you hit D to delete all your breakpoints. Big shorthand. So now if I look at info B, we see that there's no breakpoints now, and then that clears me up again for another PIE run. Let me see if I can show that failure mode happening. So if I do PIE break and then like, I don't know, something random. All right, well, I swear it works this time, but normally you can sometimes run into issues where it tries to insert your breakpoints and it goes, okay, well, I can't map the breakpoints from this run to that run, and then you have some issues. So just, if you run into those problems, just delete all your breakpoints and restart it. So now let's get back to business. I closed my IDA, so we're going great. Let's keep going. Thank you in the Twitch chat for that, by the way. We're going to fix that now. I've been informed how to use GCC by someone smarter than me. Thank you. Check sec. Glorious. Okay. Now we're probably fine to demo that. I do have to reload it in IDA, though. do. Main, decompile, all the way down here. All right, now we want to break at a point that we actually just can't break at. So once again, if I mouse over something, what we're looking at is the address offset when it's loaded, so 19FF, and then also this number over here will show you the actual offset in the file. Both of these are useful. They can be different. Just note that. Like, for example, if you rebase your binary to a different address, then they will be different. So let's GDB. And then I want to put a PIE breakpoint at 19FF. I'm going to run that. And then now I'm at this wonderful location in our stripped binary. And essentially what we can do is we can now look at what's actually happening here. So we're passing this just one argument, which is this art pointer in RDI, which is pointing to these two characters that v2 has set here, which that is the 6824 that we were talking about earlier. And if we go in and look, we're assuming that this is just going to dereference the pointer and return it. But if we step into this function, we can start reasoning about what's happening. Come on. Trying to make it small enough so I can see my registers, which might not be possible, but oh well. So we'll step. We know that our first argument is going onto the stack right here. So remember that RDI is the pointer to that input. So we're going to keep stepping. Then we're also seeing, so we note that there's no longer a stack canary, I guess. So we're not seeing that anymore. And so we're loading that pointer back into RAX. So we're seeing that pointer here. Then we're going to be loading those 2 bytes from that pointer into EAX. So we get 6824. Then we're storing them back onto the stack and then loading them back again. 6824, and then we're going to pop and return. And then boom, boom, boom. Come on, go back. There we go. And so now that's going to go on the stack. And then we get our predict the mystery string. Oh, I should not have stepped into that. Finish. And then we get our scanf call. And essentially, I'm going all the way down to where this check is happening, just because I want to verify my assumptions. So we observed this 6824. Oh, come on, come back. OX 6824. Then boom, boom, boom. So let's see, we're going to continue. Oh, I missed it already. We just passed our comparison. All right, this is a long-winded way of basically saying, before I get super off in the weeds, is basically the point is that these can be misleading. And essentially what happens is, I'm pretty sure my demo is running into an issue here, because what's supposed to happen is they're supposed to endian swap, but they're not endian swapping. And so I think I broke something somewhere. The point being is that you can have behavior in the decompilation be abstracted away when IDA tries to make assumptions about it. In this case, what is supposed to be happening is it's supposed to be endian swapping this 6824. I'm pretty sure because I just didn't just O0 this, it might be optimizing that away, but we'll see. Long and confusing demo, but any questions about this part? Basically, decompilation can lie, verify your assumptions. And this will come into play when you do like cows and bulls, some of the later reversing challenges, when you even do Yon 85, like there can be misleading things. Like other common like sources of headaches that at least I see from time to time is, remember that when you're in IDA, you can change data types around. So this number looks great when it's in hex, but sometimes IDA will go, okay, that's not a hex number. That's actually like characters, like $. And then all of a sudden your brain is going, oh, that's a string, that's got to be important, when it's really just 2 random hex characters. Similarly, like never forget like decimal hexadecimal conversions. Those kind of things also can really trigger nightmare scenarios. So the next part of the demo that I kind of wanted to go into, and let's do it like this. Let's keep skipping around. So The next thing I really wanted to dive into is structure shenanigans, which is essentially looking at data types in IDA. And so this one is a little bit more complicated. Basically, we're given a second menu, a menu behind the menu, where we can add, view, or check things. And if we add things, we can enter an ID, we can enter some data, and then I guess like we're given the ability to view things. So probably shouldn't put a U in there. Essentially, something interesting is happening here, and then I have this check option that is opaque in nature, meaning I'm going to have to reverse it to figure out what's going on here. So let's dive back into main, and then I'm going to come down to my third option here, just because that's what I was going for, structure shenanigans. So v9 to 3, and then I'll rename this, so op3, something like that. And here we start to get some interesting stuff going on. So let's close that out. Can't get rid of anything else. Okay. So we've got our menu, and then we've got a couple different options. We have the ability to add things, which it looks like adding calls some functions and then presumably adds a node to this system that we've got going on here. I've got a view option, which it looks like it's calling a function and then calling puts on something. And then finally, we have this v3 option for check, which looks like it's calling some kind of function. And then if that check is succeeding, that's what we're looking to get, because that's returning a 1 while everything else is returning 0. And so one of the things that we really need to get good at doing in IDA as a reverse engineer is making the data types make sense. Because when you make the data types make sense in the decompilation, it's going to become easier to read and easier to reason about. For example, right now, we can make some basic assumptions about what's going on. The first thing that we can obviously look at is that we have 2 scanf calls that are happening, or 3 scanf calls that are happening. Like we have this v3 variable that's obviously like our menu variable. We have this v2 that's in our little add section right here that's taking in a number. And then we have a data that's being taken in, which 31s, which that means we can input a string up to length 31 plus that trailing null byte. And then we're passing them into these functions. So right away, I might come in and say, okay, well, this is going to be like input ID. Maybe this is going to be like input data. Just because, once again, I'm just going off the labels. Like we don't need to do complex, like hardcore amounts of reasoning to go like, okay, what are these exactly named? Just run with it. Pick something and run with it. And so we can start diving into it. And then right away, we're presented with a kind of nasty looking function that looks like it's doing some memory allocation, some other stuff. It looks like we've got a pointer that's being allocated with malloc, and then a whole bunch of things in this pointer are just being set at random. Now, to me, as someone who, 1, wrote the program, so it's kind of unfair, but 2, has reverse engineered a lot, this to me is looking like a structure. And the way that you can kind of quickly pick out structures when you're reverse engineering is looking for pointers that are just like constantly being accessed at random offsets. Other ways this can happen is maybe you embed the entire structure into the stack rather than just a pointer to it. So you'll see like a char array that's like randomly very big, and then like you're randomly indexing into the middle of it constantly. And so this sort of just becomes like a puzzle game at this point. And IDA can kind of help us solve the puzzle game a little bit. So we're seeing that v3 here is being used a lot. And so I want to go ahead and make a data type and start basically storing pieces of information in that data type, and then just slowly building up what that structure probably eventually looks like. Because it's very likely that when you have a structure, it's not going to be used like end to end in one function. Instead, it's going to be like, okay, you have this function that does this thing with the structure. You have this function that does this other thing with the structure. And they're usually like orthogonal in nature. And so you have to like combine like your knowledge across multiple points in the program to fully reverse them often. And so the way that we work with structs in IDA is if we go up here to view, open subviews, and then local types. This is basically like the God interface for messing with data types. And it's because what we can do is we can go in here and just add a type and then just start typing C syntax. It's beautiful. So if we go struct and then, I don't know, we figured it was like a node or something. And we don't know anything about this struct yet. So I'm just going to leave it empty for now. And I'm going to put my local types kind of over here because I want to be able to modify this quickly. And so right away, what's something that I can discern about my hypothetical structure?
Variables inside.
Sorry?
Variables inside, like the values.
Yeah, so like right away we have 3 like accesses, right? So we can assume that there's maybe some variable or some piece of information that's stored here. Is there anything else that we can discern about this struct just from looking at this one function? Yes. Bingo. That's the first place I'm going to start, which is that I have a malloc call with a fixed size, and then it's being set equal to v3. Now, we also know that this function is being called in the like add a node like structure. So presumably this malloc call for me, I'm making the assumption that this is creating a new like node structure. And so I'm going to come in here, and if I just double click on this node, or it's like Control E to edit it, I'm going to start simple, and we're just going to say that we have hex 38 bytes of data in our structure. And so then I just need to come over here and properly type this. So we call this structure node, just like that. And so I just went ahead and updated all of these references to go through and sort these out. And now my job is to kind of fill in things where it kind of makes sense to fill them in. So the first thing I've got is I've got this v1 data or v3 data being equal to a1. We know that based off the call site of this is our input ID, and the second argument is the data. So I'm going to name those appropriately. So we'll say that's the ID, and then this is going to be data. And right away, we've got 2 of our struct members that just instantly fall out of this. So v3 data, so this is probably going to be the very first member of the structure, is ID. And then the next reference that we can find to this structure, like sequentially, like in the order of the structure, not necessarily the order of the code here, is at 4, offset 4. So that makes me think that if I come in and edit this, I have presumably some kind of integer right up here at the top. Note that I'm not 100% concerned with like getting the right data type. The thing for me right now is the size. And so I'm just going, okay, what's a 4-byte thing? Okay, int. And then we'll just call that ID. And then similarly, because we know that this has to be hex 38 in length, I'm going to come in here and drop that down by 4. And then, boom, instantly our decompilation's gotten a little bit better. And so we can continue doing this with all these different entries. So here we have a stir copy v3 data to data. Okay, well, that looks pretty reasonable to me. And then we have a usage on 44, and then another one at 36, which seems to be a pointer to this. So this is something where like, I'm just going to make an assumption and move on. So I'm just going to label both of these fields. Like I don't necessarily know what they're doing yet, but we're probably going to see more usage of this structure later. So I'm not going to sit here and like really struggle and reason about like every single bit in bits in like Bob or whatever it's going on. And so let's see. So we have this goes at least to 36. So we'll say 36. And then it's telling us that this at 36, the address of this is getting set to a dereference. Let's see. Address of this, dereference, so probably whatever this is. And so I'm just going to assume that it's 8 bytes. Let's go long. And then I'll just call it something. Like, don't need to go crazy. And then finally, I have one more to go. So the one at this offset of 44. So, and then I guess I'll just call this something else. All right. And so now we've got a very simple looking function here that's no longer a nightmare to reason about. And the nice thing is now, because I've got this one win, like I already know like kind of what the node structure looks like. We also know, because IDA is telling us that this is returning that v3 pointer, so we can go back and start retyping things and just kind of let the decompilation like settle, for lack of a better term. So we know that this was presumably like make node or something. And then this v4, we know that it's a pointer to a node, so we can retype it. So we'll say like struct node pointer. And then similarly, I guess I'll rename it to like node pointer or something like that. And then we can continue tracing this around. So node pointer instantly flows into this 12d8 function. I can come in here and instantly retype this pointer to be a struct node pointer. And then if we also just kind of do some very strict reasoning, we can see that we're returning A1 and it's being converted to a struct node pointer at the very bottom of our function. So that instantly tells me that the type of the A1 is likely going to be that struct node pointer because A1 isn't being written to at any point during this function. Like I'm not seeing like A1 equals something else. And note that I can also comb through the disassembly to make sure that that's the case. So struct node pointer. And now we're starting to see our decompilation start to make a little bit more sense. We can see that there is an inserting function happening here where it's comparing the IDs of A2 and A1 and then making a decision about essentially where this node is going to end up. And it's looking like something else and something are both pointers to more nodes. And so right away, like what kind of data structures do we have that use nodes with pointers? So like a linked list, there's tons of these types of data structures, right? Like this isn't the only one. But like a linked list is like a great assumption. So like maybe we could like say, okay, well, this could be like forward or something. And then maybe the other one could be backwards. Because I mean, we have 2 pointers, so it doesn't make sense that just like a next pointer. It could also be a tree. I hope that's how you spell forward. And then we've got another function being called. It looks like this is actually being called recursively. And so this would be the kind of thing where it's like you could start to extract these algorithms, figure out what's going on, and sort of start to reconstruct what's going on here. In the interest of time, I'm not going to like fully go through that just because I want to get to the rest of these like subsection of demos. But does anyone have any questions about like the process of using IDA to like kind of like insert a structure and start to apply it? Okay, I want to show you one other nice thing that you can do, which let's say that this is the very first function that I looked at in this entire program. So one thing that's nice about IDA is that when IDA, there's sometimes a, oh, come on, it's not showing it for that one. Where's a good one for this? Maybe in here. Aha. So sometimes when IDA can see enough references to a structure in one function, IDA can go ahead and attempt to automatically kind of generate the struct for you. And so this is something that I will constantly use because it honestly just kind of works most of the time. Not as in it magically gives you the answers, but it just saves you a little bit of pain. And so in this case, like A1 is obviously being referenced at a whole bunch of different offsets. And IDA knows this too. And so sometimes when you have an argument like this, IDA will give you this option to create new struct type and then give you a structure with all the references just automatically labeled as different variables. And so in this function, IDA was like, okay, well, we saw A1 being referenced at offset 40 and offset 48. And so it said, okay, well, we got a 40-byte gap. I don't know what goes there, but then we've got 2 other keyword values. So those 2 8-byte values at the bottom there. And then that's a very easy place to just instantly start reasoning about my structure. Now, the one word of warning when doing this is that IDA does not have information in this function about how big the structure A1 is. It's very possible that there could be even more structure members down here that it doesn't know about because it literally just doesn't see them in this function. And so one quick way, if you know that a function is being used in a lot of different locations, is to just generate it in a couple different locations and go, okay, here's all the uses, and then just kind of merge them together, which is unfortunately a manual process, but type 2 fun. Are there any questions about this before I move on? Is there anything where we're like, oh, I don't know how data types work? Actually, let me cover one other thing too, which is that keep in mind that you can really go in and perform invasive surgery on these data types when they don't make sense. And in this case, they're fine, but sometimes you're going to come in and find cases where, okay, maybe input data isn't just like a clean 40 character buffer, and instead you have like 4 or 5 stacked like 8-byte integers that it's treating as a buffer for some reason. So don't be afraid to come in and brutally mess with your data types to try to get results that you think are accurate. When you do something like this, it's like maybe I decide that this isn't just 1 character array. Maybe I decide that it's 2. And then I need to like insert a new, oh, there's normally a way to, normally I'll insert something else for you, but let's do it like this. Interesting. All right, well, normally IDA will insert something there for that. But basically, there are times where you'll sometimes need to merge stack variables together. It's very rare that you have to like break them apart like that, but it is common, especially like in like binaries where you have like stripped symbols, and then also just like O2 optimization. Really start to get some nightmare scenarios where you're going to want to go in and start performing surgery. Okay, so I've got 20 minutes, I think. Let's get one more in here. So let's see. So I've got 3 demos. We can probably get through one more. One of them is about utilizing basically like things that are already in the binary. So for example, say that you have like some table that you need to dump out of the binary and then start reasoning about that instead. So that's one thing that I could talk about. I could also talk about like what to do when you have like very scary looking transformations. Basically, or actually, I'll talk about that one really quickly because it's like 30 seconds, just going over like a trick. So every once in a while, you're going to run into situations where things look like a nightmare, but they don't have to be a nightmare. And I'll give you an example of that in this transformation terror. Essentially, what I've got is a function that is performing some nightmare input transformation on your input. And when you have something like this, it's not always the guarantee that the fastest way to go about it is to like take this, dump it out, reason about like how to undo the transformation one step at a time, because it gets really annoying. And sometimes you have transformations that are literally nonlinear in nature to where you can't undo them. Or at least undoing them becomes prohibitively difficult. And so every once in a while, you're going to run into situations like this where you can work smarter and not harder. And what I mean by that is if we run this and look at transformation terror, and then I input like, let's say it's taking read 8. So let's say I input 8 A's. So 1, 2, 3, 4, 5, 6, 7, 8. And in this case, I get a response back. And then maybe I put in 1, 2, 3, 4, 5, 6, 7, and then a B. And then I get a different response back. And then maybe I put some different data in here. The point being, though, is that if you ran this enough and started studying some of these outputs, you sometimes run into transformations where 1 byte of input is equivalent to 1 byte of output. And you run into these situations where the transformation can essentially just be treated as like a black box. And you just make all the observations and just remove the black box. And what I mean by that is, let's see if I can find a value that like prints nicely. Let's say 1. Yeah, there we go. Okay. So if I put in 8 ones. Oh, come on. Let's see. Okay, these are printing to non-printable ASCII, so let's use Python. That's not how I spell that. 3, context, Python from star. I'm going to use the log level debug to show you what's going on here. Send line, what was that option? I think 2, right? Yeah, okay. So if I send, and then let's go 1, 2, 3, 4, 5, 6, 7, 8. Nope, that's 8. And then I get a receive back. I can see that I'm getting a set of output. And then if I send in that, basically that exact same input again, what you're going to notice is that essentially after a while, wherever your character is in the input, you're always going to get the same character in the output. It's essentially a cipher. Like, it doesn't matter like what the details of the cipher are. Like, you have 1 byte of input gets you 1 byte of output. and it doesn't get shuffled around. So essentially the input of A, so like 8 A's, the value is going to be the same in every column because it's the same transformation that's being applied to every single byte. This means that we have like a linear transformation where no matter where I put in an A, I'm going to get the same output no matter what. And when you have cases like this, you can essentially bypass it by taking the entire input space and then observing the entire output space and then just building a map. Like basically just a Caesar cipher lookup table, essentially, where it's like, okay, what input letter maps to what output letter? And then you look at the big, scary black box in the middle and go, okay, I don't care about this anymore. Like, it doesn't matter how freaky the transformation is. It doesn't matter what kind of like SHA-256 like hash nightmare they unleash on you. If you can put in one character of input and get the same character of output, regardless of where you are in the string, like just observe it and then make a decoding table. Does that process make sense? I can explain it a little more if like what I'm trying to explain. The demo here is a little bit, the visualization part is lacking. But does that kind of make sense, like the thing that I'm getting at? Okay. So then let's cover our last one, which is data dumping. So there's going to come times where you also want to use things in your binary. For example, there is common like substitution tables, like lookup tables, jump tables, or just like program data that might happen to be important. In the example of like the cows and bulls challenges that we put on, if you've looked at them already, you'll know that like those challenges load a game file that's just in the challenge directory, for example. But what happens if that game file is like embedded in your binary and you have this important binary data that you want to get out and use like in your solving scripts, right? So let's look at a case like that. So if I head over to this data dumping, I have what probably boils down to the most dumb demo you'll see this entire semester, which is I have a memcompare where basically I read in 100 bytes, and then I compare those exact 100 bytes that you just sent in to this symbol here, unc40EO, which it turns out this is just an array of data that I've just stuck in the binary, and you just have to guess it. Now, if you didn't have the binary, this would probably be impossible, but you do have the binary. And so this means that we can leverage this data in our script rather like, because like I could sit here and like scribe this out by hand, right? Like OX3A, OF7F, or I could like copy and paste this whole thing and then like start like doing surgery in Notepad or like, I don't know, like give it to ChatGPT and be like, please. But like, we're more intelligent than that. And so what we can do is we can just load up this data in our Python script and just kind of send it to the program. And so I wanted to quickly show off like how to do that and just one pitfall to avoid, which is what a lot of people are going to do is they're going to go in IDA and go, okay, well, this unc40EO symbol is at offset 40EO. And so therefore, if I go into Python, and then let's say that I open the challenge. So I'm going to literally open up the challenge binary, RB for read bytes. And then we'll just store all that data. And they go, okay, well, my data is at OX40EO. And then I know that it's going for 100 bytes, so OX41EO. And they go, okay, well, that should be my data. Oh, crap. Where's the data? And so this is just one thing you have to keep in mind is that IDA is going to try and load things in the way that they would look in the memory of your program, not necessarily how that is represented like on the actual ELF file on your hard drive. And so this is where the stink about like basically the two different types of numbers down here in the tooltip comes into play. So we have this 40EO, which is saying, okay, that's where it would be loaded in memory. But then this little value over here in the bottom left where my mouse cursor is, this 30EO, that is the offset in the actual file on the drive. And so we could confirm this also just if we didn't want to like blindly trust IDA, like you would use readelf for this. Because we're looking at the data section or data segment in our program. And if I run readelf on it, we can find that data section in here somewhere. It's one of these right here. And we can see that there's that 1000 offset difference, which is why you're seeing that hex 1000 offset difference in IDA. And you could do the math between those sections as well, but generally IDA is trustable in this situation. Just know that there is a difference between these two numbers. And so because of that, when we come in and read this, instead of 4 OEO, we really want 3 OEO. And now I have all of that data in my binary. And so we could verify this. So P equals process, P dot interactive. Let's go to transformation terror. Let's see if I can get away with just P dot send. Oh, I went down the wrong one. Data dumping. There we go. That's what we want. Why? Okay. Come on, P dot receive. There we go. Okay, why isn't that working? Everything's falling apart. Mayday. All right. So we're going to verify our assumptions. Memcomp buffer hex 100. Let's GDB things up. It would probably very help if I put this in a script, but we're in too deep. Oh, I need that context.terminal line. Oh, short workflow tip. Control R is the only keybind that you'll ever need to remember. Pretty much in like most terminals or REPL like type systems, hitting Control R will open up this thing called iSearch, which basically just lets you search through your history like dynamically. So I pulled up this context.terminal line by hitting Control R and just looking at like context. And then I don't have to remember it every time because it's in my IPython history. This thing also works just in bash. So if I Control R and like look for my, like, for example, the readelf command that I just ran, I type RE, that's the command that matches. I pull it up and hit enter. Just Control and R.
But what if you have like multiple commands, like context.debug, context.
So then it'll basically match the closest one that is the most recent one and then the closest. Yeah, so if you use the arrow keys, you can switch between them and kind of go through all the matches. Or if you just know, okay, I need to go to the one that's like context.terminal, you can just keep typing until it pops up. That's generally what I do. But yeah, short workflow tip. And then now let's dive into this and look at what's actually happening and what assumption I'm making that's obviously not true. So gdb.debug. And then let's see, I'm going to continue over here. p.sendLine. Let's make sure I'm going down the right menu. Okay, need to go down number 1. p.sendLine 1. Let's receive again. Why are we waiting? That should not be happening. That's not paused. Oh, okay, I see. It just doesn't send output. I'm a genius. There we go. And then now we'll try and send in our data and see what's actually going on here. Note that I do need to put a breakpoint down before I do this. So you're running into, we're really diving into the holes here, but you can very quickly see how annoying it becomes to debug strip binaries because I can't just set a breakpoint in here. And so this is why the PIE run stuff can be really useful, because I can use gdb.debug with like gdb script, throw in the PIE breakpoints, use the PIE run. You can really optimize your workflow together if you spend some time sort of like studying the glue. And so I would highly recommend like just spending some time messing around with like some of those PIE commands. we can come in here and use GDB script to set like a position independent breakpoint. So I really want to break on this mem compare, for example, because like obviously the values that I'm putting in are not the values that it's expecting. And so we could break at this 179D value right here. 7D. And then PI run. I don't think I need that semicolon at the end there. Oh, come on. Okay, break. List index out of range. Why? All right, there's 100% a way to do this that I'm failing to obtain. Do I have to gdb.debug? There's probably something I have to do to make it so it doesn't start the process right away. Exceed non-GDB args. Script attaching. All right, I will investigate this offline and then post a snippet in the Discord of exactly how to do this because it is 100% possible. In the meantime, let's do it the slightly old-fashioned way of going in. Where did my stuff just go? There we go. Data dumping. I closed my IDA. What was that address that I needed? PIE 179D. Data dumping. Let's just throw in some A's for now. All right. And then, so other things that we can do to dump out data is just drop in like a lot here. There is also other ways to dump this out in GDB. So So for example, if you wanted to just copy and paste this out, this is very easy to doctor up. There is also, I believe, a dump command, which we can use to dump, let's see, memory. Then we want to dump from here. And then I believe it's to an end address, which is this 1EO. And then let's see. Let's look at the man page. File start stop. There we go. That's what I'm missing. So, oops. I need to put this in my home directory, but let's see if we can just get away with that. No. Okay. Let's see. There we go. So that's another way that you can dump memory out of GDB. So also a very, very useful command. So I'll show you what we just did. So we just created this DMP file, which is in theory those hex 100 bytes that I need to send into the program as well. So let's also try that one as well with open and let's get this over the line. Come on. As f d equals dot read. Oh, what did I just name it? Hello? Oh, that should be a read. Interesting. I'm in /challenge, that's why. There we go. Okay, now let's try sending this in. Where's my... Always got to use the Control R. And then we should be able to just send in this data. There we go. Okay, now I see passed. That is, come on, print.decode. There we go. Now we've passed that check. All right. little bit scattered of a demo. Any questions to kind of round out? And yeah, for the Twitch chat, attaching is easier, but it's only possible with sudo GDB. So if you're willing to hop into practice mode, like that's another way that you can address this, but it does make your process a little bit more non-transferable because you can run into some minor quirks. All right.